Okay, so this brings us to the start of chapter 2. Does anybody have an idea what this is?
Bubbles.
They're
Is this
bubbles.
oxygen?
They do contain atmospheric oxygen and nitrogen. You could see this if you peered into a relatively clear cocktail.
Ice?
It is ice, right? And so what are those spherical things in there?
Is it trapped air, like an ice core?
Exactly. So when water freezes, it forces the air out, right? And it can't be dissolved in there anymore. The oxygen and nitrogen can't be dissolved anymore. So yeah, it's trapped. And then the last question for you is, why is it spherical? Water tension, go Lane. Yes, exactly. Uniform pressure, both those things. The water tension basically holds the edges of bubbles together, and it's the shape that has the minimal. It takes the minimal amount of surface area, minimal energy per volume. So we're going to go into the properties of water now. We'll start with chemical and physical properties, talk about water viscosity, inertia, and physical parameters, movement of water, and then forces that move water. This class is generally organized from the basic physical stuff up to the more complex factors associated with the organisms. We'll hit the organisms taxonomy sort of a little bit earlier on, just so we know what the players are in the game. So there's really important chemical and physical properties of water. Water is a fairly unusual compound because of hydrogen bonding. It has high density, it has high surface tension, high heat vaporization. It takes a lot of energy to heat it up, high heat capacity. It's liquid at the Earth's surface. It's an excellent solvent. It's really important for weathering. It drives global biogeochemical over geological time. So we can talk about a few of these things real quickly. Density. Does anybody know how we define a gram? What a gram is?
Isn't it 1 cubic centimeter of water?
Exactly, right. So one of our basic units of measurements, a gram, is based on 1 cubic centimeter of water at its maximum density. And we'll find out what temperature that is at in just a little bit. All of these things, surface tension, heat of vaporization, all are related to the fact that there's hydrogen bonding that's holding water together. Can anybody think of other compounds that are liquid at the surface of the Earth under normal temperatures? I mean, there's lava, but that's not normal. I mean, that's normal for a volcano, but for most places it's not. So it's standard atmospheric temperature and pressure. Are there other compounds that are liquid?
Yeah, mercury.
Mercury, we've got mercury, yeah. There's another class of compounds that is liquid. Oils, good. Oils and alcohols, right? So there's organic compounds. Other than that, most of them are not liquid, and they're not very abundant. So it's really important. In addition to those properties, ions tend to be more soluble in warmer water. For the most part, there's a few that aren't, and gases are less soluble. So when we were at the lake yesterday, talked about oxygen solubility in water, and the warmer water gets, the less oxygen there can be in the water. So that's why the amount of oxygen in water is a function of the temperature. There's an unusual relationship between temperature and density, which we'll get to right now. So here's a graph of temperature in degrees centigrade versus density. And as I said, right, 1 gram is 1 mil at the maximum density. And so it's exactly 1 at about 3.9 degrees centigrade. And then as you heat up water, it becomes less and less dense. So we saw that at the lake yesterday, where there's a little bit warmer water sitting on top of the cooler water because it's heating, the surface is being heated by the light, and it's warmer, and so it'll just stay sitting on the top. Now, there wasn't a very big temperature difference, so if a big wind came, it would have knocked that apart, but we'll talk about that more in a little bit. So there's this break in this graph right here, right? And all of a sudden we're jumping a whole bunch of units. And then we're right down here, much less dense than water is at any temperature, even almost all the way up to boiling. So what is that? What's happening at 0 degrees that's leading to water to become much less dense?
The freezing.
Exactly, it's ice, right? So ice freezes and it floats. It sits on top. And that's an absolutely essential property, a very unusual property, that the solid form is actually less dense than the liquid form. But it's really important, because if it was not true, most of the water would be locked up in the oceans, because once it froze, it'd go down to the bottom and just sit there frozen, right? So it's a really important aspect of the way water works. The other thing, we can see that this curve's not straight right here, that it's actually falling off more and more quickly as we go up here, right? And so this next graph is a percent density per degree C increase, right? And we see that what's happening is that density decrease is happening faster and faster. And this will be important when we talk about stratification of lakes, in the tropics in particular. So there's the maximum density of water, and we can see these two rates. Now what this graph is showing is that this rate right here is not as high as this rate is right here. And here's another version of this, of the same graph, where now we're going all the way up to 80 degrees C. I mentioned that ice and no break, right? So ice is still less dense than water when you're almost all the way up to boiling, right? And then we're zoomed in a little bit without that break here, and we're zoomed way in right here. So we're going from 0 to 10. And this is another point to be made, is that, you know, the maximum density is right here at about 3.9, or we could say 4. It would be fine if you said that at standard temperature. But what happens here is kind of curious, because it's, as you get colder, it's starting to get less dense, right? So water that's colder than 4 degrees can float on top of 4 degree water, and water that's warmer than 4 degrees can float on top of 4 degree water. What's happening here is those hydrogen bonds are basically, there's weak hydrogen bonding between the water until you get up to, you know, boiling, and then eventually it's all flying out in the atmosphere, and it's not there very much anymore. As you get cooler, it gets more and more dense, right? But then as you get below 4 degrees C, you start getting those hydrogen bonds forming the structure that ice will eventually have, and it starts opening up because it's starting to form that crystalline structure, albeit transiently. So it's starting to actually become less dense, and those hydrogen bonds are starting to order things more and more and cause the density to decrease. In addition to temperature changing the density of water, the amount of salts also have a big effect. And so we have right here, seawater is this point, is this point right here. And we see that the density of seawater is 1.025 or so, like that, right? So if we go back to this graph, so think about 0.01 difference in density. These differences up to 40 degrees are in the 0.001, so 10-fold less. So if you have saline water, you can basically stratify a system and go against these temperature things. So that'll become important too when we talk about saline lakes. And anybody tell me what this is? Good, Abigail, water strider. And why is it there?
Because it holds water. Tension allows it to move across the surface of the water.
Right, so it's one of a number of organisms that can use water tension to stay on the surface of the water, and it's specifically adapted to using it. You can see it's pushing down in there, but that the hydrogen bonding is holding that surface tension, and it's sort of depressing it a little bit. So this is a spectacular picture. Okay, so I've got a question of the day for you all, and I think you all have your names on your screen. So just go ahead and chat, throw your answer in the chat, and that will record your name, and I'll be able to use it for your attendance question of the day point. All right, so now everybody's had a chance to answer in the chat. The first one, maximum density of water is at about 4 degrees C. That's true. Ice is more dense than cold water? No, it's less dense. It floats. Density decreases at an ever greater rate as temperature increases from 4 degrees C. That's also correct, and that was the graph where I had the two lines as it went up. The units of a gram are based on water at its minimum density. No, it's based on water at its maximum density. So that D is incorrect. So now we're going to get into some stuff about Reynolds number, and this is stuff that perhaps you've not had in other places, but it's really important as far as the way organisms have evolved to operate in their natural environment. And it tells us a lot about the way systems work. And the reason for this is that hydrogen bonding tends to become more important at smaller scales. And this alters both viscosity and inertia. So if you think of the hydrogen bonding being this little net thing that's holding things, and you think of something like a fly pushing through a spider web, right? Use that as an analogy. Fly can't push through a spider web. It gets stuck. We just walk through it and go, spider web, right? It's because of the difference in scale. The same thing is going to happen if we have a bacterium trying to swim through water, or we swim through water. Right, it's going to be more resistant and feel more viscous. Viscosity is a resistance to change in form. It's a form of internal friction. And inertia is a resistance of a body to a change in its state of motion. So you probably all know about inertia. Reynolds number incorporates both these. So Reynolds number is a unitless number that describes fundamental properties of a fluid that are based on scale and how the object that's moving through the fluid and what the density is. So here's some equations. Don't panic because you can go look these up again easily. The first, viscosity, is this is a function of the dynamic viscosity. So dynamic viscosity is sort of the intrinsic viscosity of a fluid, regardless of scale. And we could think of some fluids like we use corn syrup as an analog for a very viscous situation that happens at microscopic scales. But oils are more viscous than water. A lot of heavy oils are, like gasoline's a little bit less viscous than water. So the viscosity becomes higher as the intrinsic viscosity is greater, as the surface area is greater, as the water velocity is greater, and less with a longer object. So we'll think about these in practical terms. The first is viscosity as a function of surface area. So when you're in a car and you're a kid and you're going 50 miles per hour down the highway and the window's open, what do you do with your hand?
Stick it out the window.
You stick it out the window, right? You stick it out the window and then you do one thing, right? You stick it out the window and then you turn it like this. And two things happen. One, you put more surface area. And the second thing is Bernoulli's force. the air is going over faster over the top than the bottom, and it pushes it up, right? And then you do this, and it pushes it down, right? Also, think about if you're wading in a stream. If you're wading upstream into the water velocity, right? You have more viscosity than if you're wading downstream. If you're trying to pull something upstream with a big surface area, it'll feel more viscous than if you're trying to pull it down. Okay, so there's the water velocity. Higher velocity feels more viscous. Higher surface area, it feels more viscous.
What did you call that principle where it's like the wing and the air goes?
Oh, that's the Bernoulli effect, right? So if you have a wing where if you have fluid flow that's faster over one side of an object than the other, it pushes it towards that.
That's like bird wings.
Bird's wings, airplane wings, yeah.
Okay.
And then characteristic length. That what happens is if you have a long object, it's less influenced by the viscosity than if you have a short object. So this is why we have javelins, right? Javelins can go a long ways. They want to minimize the viscosity of the air they're going through. And that to do that, they make themselves long and skinny. So they have minimal surface area in the front and a lot of length. And here's where if we're in a classroom, I throw the pointer sideways or the other way and everyone laughs, but that's not going to work online. So sorry about that. The next, so that gives you sort of a physical description of how viscosity works. The second one is inertia. And you can think of inertia as being a function of the density of the object, the surface area of the object, and the velocity. So let's start with a softball and a shot put, assuming that they are the same size. And I'm going to throw a softball at you or a shot put at you at the exact same velocity. Which one would you prefer me to throw at you?
Depending how far away you are, probably the softball.
Right next to you at the same velocity. It will strike you at the same velocity.
Softball.
The softball, right? Why? Because it's less dense, so it's going to have less inertia, right? That's why, you want to play with Nerf balls with kids, not hard balls, hard baseballs, right? Same thing. Okay, so that's how the density works in that. Surface area. You have a bigger surface area and you're going to have more inertia. So if you are swimming in the ocean and a big wave comes at you, right? You want to dive under it, dive through it, right? If you stand there, it'll slap you, hit you with a full surface area, and you'll get that full force of the wave. Or if you have a little water balloon or a big water balloon, the giant water balloon hits you and it'll knock you over. Little water balloon, fall, right? And then velocity is a fact of related to the square of the velocity. This is why it's so much worse to get in an automobile accident on the highway than it is, and it's not a linear relationship between 30 miles per hour and 60 miles per hour, right? It's squared worse. It's not just twice as bad because you're going twice as fast. Okay, so you put these two things together and you get the Reynolds number as a function of the density, the velocity, the characteristic length, divided by the dynamic viscosity. So let's talk about this in practical terms about aquatic organisms. So the first one is how viscosity varies as a function of temperature of water. And so we see at 25 degrees and 30 degrees, which is where we were at the Willow Lake yesterday, that the viscosity relative to 0, right, is about 0.75 as opposed to 1.75. So it's almost, 1.5. So it's almost twice as high when the water's cold than when it's warm. That means when you are a fish you are much less, you need to expend much more energy to move through the fluid when it's cold than when it's warm. So what do most fish do around here in the winter? We will not talk about the trout that they stock in there just in the winter, but we'll talk about some of the native fishes. What's the sort of the main thing that fishes do in the winter as opposed to the summer?
Is it like
Lower their metabolism, Cassie said. Good.
They
Cool.
stay in one spot.
Yeah, they hang out, right? They don't do much, right? Why is it? Because there's this balance between stay close to the bottom, right? They don't move much. They hide. They don't hunt much. They don't move around a lot because it takes a lot of energy to move, number one. Their metabolism's lower, so they don't need as much energy, right? So it'll take more energy to find food, and they don't need as much. So all they do is they slow it down. And that's because, in part, because of the viscosity. Now the trouts are evolved to lower temperatures, and so they've specialized on that. And that's why they do better in cool water than warm water. They still have the same effect though. Technically, they could swim faster in this warmer water, and they'd swim as fast as they could to get to colder water if you put them in it. So we have these various organisms here that are on the Reynolds number axis. So we're gonna talk about what the Reynolds number axis, the organisms that are found in freshwater, are operating on. So bacterium are about a micron in size. They are they can go about 10 to the minus fifth meters per second, and they are really low Reynolds numbers, about 10 to the minus fifth. On the other extreme, salmon, right, are pretty big. They're like a meter, bigger than a meter, can be, and they can swim pretty fast. They can swim maybe 10 meters per second, right? Maybe not quite that, but certainly more than a meter per second. And so their Reynolds numbers are running around 10 to the 7th. This leads to a bunch of different characteristics of the organisms. One of the things that is really obvious is that the salmon has a different shape than these organisms, and the bacterium can be almost any shape. We'll talk about that a little bit. So why does viscosity decrease with increased water temperature?
Is it a relationship with density?
It's related to that. Why does density decrease with increased temperature?
Because the particles are farther apart? There's less to get through?
They're farther apart. Yeah, there's less to get through, and there's less, one other thing. Hydrogen bonding. Yes, exactly. There's less hydrogen bonding, right? So that hydrogen bonding becomes less, so that resistance to moving through works. Okay, so now we're going to talk about a small organism and what happens with varied by scale. We have Reynolds number. Small organisms have low Reynolds numbers, and large organisms have high Reynolds numbers. Viscosity is high for a bacterium, and it's low for a salmon. Inertia is low for a bacterium, and it's high for a salmon or us. So if inertia is really low, you can't coast. If a bacteria stops swimming, it will coast an angstrom, like the diameter of a hydrogen atom. That's how viscous and low inertia things are for them. If a salmon stops swimming, it will coast for, I don't know, 20 meters or something like that, right? I mean, that's how a lot of fish get away. They burst, and then you watch them, they just glide off. Well, that's inertia. We'll talk about water movement. Flow is going to be laminar or no flow, and turbulent for large organisms. Large organisms will streamline. Small organisms don't have to. We'll talk about why that happens. We'll also talk about molecular diffusion versus transport or eddy diffusion. So this is related to turbulent flow versus non. Small particles sink more slowly than large particles because they're in a more viscous solution. And the relative energy requirement for motility, because of this high viscosity, is very high for bacterium relative to us or a salmon. So we talk about movement of water now. At the finest scales, Brownian motion takes place. And Brownian motion is just the jiggling around of particles related to the fact that when you get to the very smallest scales, the probability that a particle is being hit on one side or another by an uneven number of molecules is higher. So basically you look at under the microscope at a bacterium and it's doing this, and that's because slightly more water molecules hit it at 1 millisecond on one side than the other, and it pushed it that way and then around the other way. We don't experience that at our scales. We're being bombarded by air molecules all at the same time from all directions. If for some reason I had all the air molecules on one side of me hit me at once, it's possible. It's highly, highly improbable, would never happen. And none of them hit me on the other side. It would just throw me across the room and splat me against the wall and I'd be done, right? And that just doesn't happen with our scales because of the numbers. So that means that water's moving and water molecules are moving very quickly, but they're not going much of anywhere. They're bouncing around like crazy, but they're not going much of anywhere. That can lead to diffusion eventually, and we'll talk about that. As we get up to the larger scale, we get laminar flow, where there's not mixing, but there's movement. All the fluid is moving together. And then as we get to higher scales and higher velocities, we get turbulent flow. So the flow vectors are not just in one direction like in laminar flow. You've got this, and the net movement is in one direction, but there's all this mixing. And the important concepts here to talk about are flow boundary layer and streamlining. So we'll talk about the flow boundary layer real quickly. And if we move towards a solid surface, the flow decreases. Well, in the open channel, we have turbulent flow. As we move into this layer, the flow becomes laminar and it decreases. So the closer you are to a solid surface, the lower the flow is. At some point, you hit the no slip zone where there's zero flow, right? Where the hydrogen bonding is interacting with the surface and the water doesn't move at all. This is an exponential function. And when we get to 99% of the open channel velocity, then we can say we're out of the flow boundary layer.
What did you call that surface water thing? They're saying the top of the water's not moving?
No slip zone right at the bottom. So if you were walking on a wet floor, right, if there was not a no slip zone, your feet would go out from under you. But because there's still water between you and the floor, but the hydrogen bonding is kind of keeping it from moving, you can walk on a wet floor and not slide. Okay,